this video, we're going to look at how the quantitative risk assessment model runs. Let's begin with column B. Column B includes the years from 2015 through 2071. In columns C, D, and E, we estimate the number of fish that could pass from below Brandon Road Lock and Dam into Lake Michigan in a year. But we do that for three different size populations, a small, medium, and a large population. The values in the individual cells are obtained from probability distributions. So here's the cumulative distribution that generates this value 45 that you're looking at. This distribution that we're looking at here, this comes from the expert's inputs, in this case these numbers right here. There is a similar distribution for a medium population and a large. And as you might expect, the number of fish that could pass through this system is highly uncertain and extremely variable. So when I hit the recalculate number, you see that we can generate many different sequences of fish that could make it through our system in a year. So the next thing the model does is it accumulates or counts the number of fish. That begins right here by estimating the population size that arrives. So for 2021, for example, that number comes from a distribution, and that distribution looks like this. There's a 5% chance of a negligible population, a 95% chance of a small population. Those inputs come from here. There is a distribution for each time period. Let's take a look at 2071 so you can see the probability of a small population has declined while the probability of a larger population has grown. So in these cells we just randomly select a population size. Here we have a logic check. This is just a sequence of if statements that assures that this pattern continually gets bigger. Let me see if I can get an illogical pattern. Here's one. During the review process, our reviewers pointed out that it was highly unlikely that there would be a small population in 2021, a medium population in 2031, and then a small population again in 2071. So we built a little logic check to make sure that couldn't happen. The next thing that happens in this model is we count the number of fish. That takes place in these cells right here. If there's a negligible population of fish below the Brandon Road Lock and Dam, then no fish get through. And that was a simple assumption that was made by the experts, and it's documented on the model assumptions page. Now let's take this small row here. 2021. From 2015 to 2021, if you count those number of fish, that totals 352. And from 2022 through 2031, that number of fish is 768. And then, as you might suspect, from 2032 through the end, that number of fish is 2087. We would get different sums from the different columns. So what we want to do is find out how many fish do we have in this scenario we're looking at here. So we have a small population by 2021. So we look at the small population here and copy that number, 352. Medium, grab the medium number and copy it, and once again grab the medium number and copy it. So the last step is to cumulatively sum these fish. So through 2021, 352 fish passed through. Add to that 332, so we've got 3584 by 2031, and add to that this number of fish, and we have a total number of fish that have passed through by 2071 of 17,569. Now what we want to know is that enough fish to establish a colony? So that brings us to this part of the model right here. So by 2021, this number, which comes from a distribution that you see here, and that distribution is obtained from these values provided by our expert. So in this particular scenario, it's saying if you get 4,250 fish or more, you will have a colony. Well, what we do is we take the number of fish that passed through by 2021, compare it to this, and if this number is bigger than this number, we put a 1 here. Otherwise, we put a 0. There was no colonization by 2021 in this scenario. We had 3,584 fish, not quite enough to exceed the threshold, so we had a 0 here. And here we have 17,000 fish, not enough to exceed the threshold here, so we put a 0. And of course, because the number of fish vary and the population size varies and the threshold is unknown, we have uncertainty in this probability of colonization. Now, you notice 2071, I get one that shows up every now and again. So what I would like to know is, what is the probability of colonization? One way I could do that is calculate this 1,000 times, count the number of ones, and that would give me an estimate. But if I did a second 1,000, I wouldn't necessarily expect the same estimate. So what we did here was we ran 1,000 iterations in a simulation, but we ran 50 simulations. We took the estimate from each of those 50 simulations and we copied them here in this space. So here's what this means. In the first simulation, we had 354 instances of colonization out of 1,000. That gives us a 0.354 probability of colonization. In the second simulation, we got a different answer, 352. And then in the third, a different answer again, and in the fourth, and in the fifth, and so on. We have 50 different point estimates of the probability of colonization. If we take the grand sum, it equals this number, 0.3582, with this standard deviation. Now, knowing that I have a large sample size, bigger than 30, and I have a mean and a standard deviation, I can create a sampling distribution. Let me rescale this for you so it looks a little bit more familiar. We're going to make it go from 0.3 to 0.4. So here we have a normal distribution that shows how the probability of colonization is distributed. So we had to stop the model and run it here, and you'll notice I can get different values for the probability of colonization. Here's another logic check that makes sure that the probability of colonization continues to increase over time. What we really wanted was the probability of establishment. That would be these values here. We get them by multiplying the probability of colonization times the probability of spread to get the probability of establishment. So what I'm going to do is I'm going to run this 1,000 times just to save time. What we did with the actual model is we ran this simulation 10,000 times. So we had a sample 10,000 or 10 times larger than what you're going to see here. But what this tells us is the probability of establishment is uncertain. It could be between 17 and 36%. We don't know exactly what it is. So if we are going to report the probability of establishment, we want to show this distribution so people understand that this is not a known value. we can get the values for a 5-number summary. Here's the minimum and the maximum. And then the percentiles, the 25th, 50th, and 75th can be obtained from here quite handily. So we have the 5-number summary. What we're looking at is the probability of establishment by 2071. Let's take a look at how that compares to the probability of establishment by 2031. So I'm adding an overlay here. And you see I have this probability of establishment by 2031, this probability of establishment by 2071. I'll add another overlay so we can put 2021 on here also. And this will give us a picture of what the probability of establishment is. So there is some chance that Asian carp could become established in the Great Lakes even before the non-structural plan is implemented. But that's relatively small. There's some probability of establishment before the non-structural plan could be implemented. And keep in mind, you can always look at the numerical summaries by manipulating your graphic here. Okay, so let's close this, or let's clear these overlays, and let's take a look now at what happens when we look at other scenarios. So this is the probability of establishment under the without project condition. Let's compare this to the non-structural. So I go to the non-structural page, I go to the same value, click OK, and we see that the red distribution has slid to the left. That's a good thing. That means it's a lower probability. But it didn't slide too far, did it? So this is going to provide a bit of a challenge for decision makers to decide how much money do you want to pay for this sort of effect. Now keep in mind, we are just looking at one of 6 experts, and there are other experts who feel that the non-structural plan would be more effective. But we'll stick with this one expert now and take a look at how they see the, let's go to the electric barrier here and select our probability of establishment. And we say OK. And here we see that had a fairly substantial effect. So in a similar fashion, we can add each of the scenarios. I'm going to go to lock closure now, and we'll take a look at what closing the lock does. And you can see that reduces the probability of establishment even further. Actually, this probability of establishment here is identical to the probability of establishment before 2021, because the lock closure is believed to be possible to implement by 2021 as well. So you can see the different reductions in the probability of establishment here. What you're looking at are residual probabilities. This is the probability that we start with, the red. This is the probability that we're left with if we implement just the non-structural plan, or the electric barrier plan, or the lock closure plan. Presenting data like this is going to challenge decision makers because they're used to seeing the number and deciding how much are you willing to pay to move this red distribution to this green position. That's really going to challenge people. So this is a brave new world of decision making.